Well, hello everyone, welcome back to Adrian's Digital Basement 2. On today's video, we are revisiting the Philips Magnavox television. This thing absolutely refuses to be fixed. And it's kind of frustrating me because I mentioned this in the last video, and if you haven't seen videos, well, part 1 and part 2, I recommend you watch those first, as this is a continuation from that part. I mentioned in the last video that I always look at these TVs as being relatively simple and pretty easy to fix because this thing was made, I think, in 2003. Everything was incredibly integrated and simplified with these sets. The board looks simple. There aren't a lot of parts on it. And, well, this thing, well, as I wrote here, blows hot. It doesn't mean it blows like a hot temperature. This is the horizontal output transistor. This is the part that drives the flyback and the deflection yoke. It generates the high voltage by deflecting the beam back and forth. And in a television that is CRT based like this, the horizontal drive is one of the most critical parts of a set. There are a few things that are critical, but that is absolutely the most critical part because without it, you're not going to get high voltage. And without high voltage, you will not get a picture. No matter what else is happening on the TV, you won't have a picture without the high voltage. So as a brief recap, this TV had a few mystery jacks on the side. I don't know why they were added by someone in the past, but it turns out that the set was broken. And what someone had tried to do is using 1/4-inch audio jacks drive the deflection coil directly, maybe to try to generate like a waveform on screen or turn it into an oscilloscope or something. The thing is, as I just mentioned, you need the deflection yoke and the flyback and the horizontal drive to have high voltage. And without high voltage, you won't have a filament, you won't have any image, you just won't have a working TV. So I really don't know what was going on with that. But we determined in part 1 that the horizontal output transistor was bad on this set, and that was keeping the B+, which is the main voltage that runs the whole set, from coming up. It was basically shorting it. Well, in the second part, I did a bunch more troubleshooting, and I ended up swapping in a horizontal output transistor from another parts board, which I actually have right here on the floor. It's right here. This is a parts board from another Philips set, similar, but not exactly the same design as this. Actually, the TV this came out of looked identical, but the board is completely different, and the parts were slightly different. But I ended up trying the horizontal output transistor, and I also swapped over the drive transformer. It's a little transformer used to generate the signal to drive the horizontal output. Well, unfortunately, I had the oscilloscope on the set, and we turned it on, and it was generating a signal. Like I could see the waveform that was trying to drive the flyback and the yoke, and then the horizontal output transistor shorted. And that was the end of that. Can't really do too much more after that. And it's a transistor, an NPN transistor, but the difference between just a normal transistor and a flyback or a horizontal output transistor is it's just designed to operate at really high voltages because the magnetics that make up the deflection circuit generate these pulses that are like 1,000 volts. So as the beam is swinging back and forth, you get these 1,000-volt pulses on the collector, and a normal transistor would just be damaged by those types of voltages. So the horizontal output transistors are designed specifically to work in circuits like that. And, well, it blew. I didn't have any other spares, so I couldn't really do any more troubleshooting. Well, that brings us to this video, part 3, where I want to try to get to the bottom of exactly what's wrong. So a few things have happened since the end of part 2. A very nice viewer ended up emailing me the specific schematics for the board that's in this set, which is really cool. And the funny thing is, and you know, the reason why I couldn't find this before, and it's actually the same PDF that's on the monitor, is these Philips schematics. When you take a look at them, and you'll scroll to the top, I'm just trying to get the mouse there. So service manual, J8 chassis. I know you won't really be able to read this, but when you end up scrolling down a little bit in these, past all these warnings, there's a picture of a 19-inch version of this TV, but it's sort of a black plastic. So I don't know, it's kind of similar, but it's a 19 PR21. But then it lists a bunch of models that specifically this schematic goes with. And this TV is not one of these that are listed. There are several that are 13-inch sets, like 13 PR20C1 and PR12 or 1320C1, whatever. There's a bunch of different ones, but none of them are this one. But when you scroll through this document, these are all the schematics themselves, you end up in these parts lists. So these are just different sets here, 13 MT, blah, blah, blah. These are all the different parts that go into making these sets, because each set has slightly different variable or variances in parts, maybe for 19 inches, maybe for stereo sound, stuff like that. And somewhere in here, and I don't remember exactly where it is, it might be this one, 13MT143S. I think that's the exact part number for this TV. So it's down here in the parts list, it's just not on the cover page. So you have to search within the PDF itself, way down here in the parts list, to find the matching model number. Well, sure enough, what we have printed out is the horizontal drive section, and I compared this to what's on the actual board, like the parts of, like the part numbers, of course, of all of the components, resistors and everything, identical, complete match. Now, some of this stuff might vary slightly, of course, because there are variable components depending on what set it is. But when I looked at like this drive circuit, this all seems to be roughly the same as what's on that TV. So that's excellent. That means that I can actually figure out exactly how the whole circuit works and troubleshoot where components might be shorted, for instance, that are drawing down the circuit and blowing out the transistor. On the bench, we have my Sencor Z meter, so a capacitor inductance analyzer. And one of the things that this component can do is it can measure for shorted turns inside coils. So we just have a random deflection yoke, and I have this flyback. This is the one I took off that parts board. So I don't think this is compatible with this set necessarily. It doesn't, I mean, it physically fits, but the part number is a little bit different. So I'm not sure it's compatible, but I wanted to get an idea for measuring the rings. And I'll have to explain what rings are in a second, but for measuring the inductance and the rings between these parts, these good or probably good parts, I'm pretty sure these are good. This actually came out of a working TV, so that's totally good. This was a working television, now that I think about it. I needed the CRT for a different project to revive a 1702 actually. So this was the sacrificial stuff. And then I've taken a bunch of parts off this, even before doing these repairs, to fix other things. So that's the reason why I like to keep these boards around, because you never know when you're going to need replacement parts. So anyways, working flyback or out of a working set, working deflection yoke, and in combination with my LCR meter, which can measure inductance very accurately, oscilloscope, and the Sencor Z meter, which will give us the rings, I think I should be able to get to the bottom of what exactly is wrong. Because when we look at the schematic, this is the flyback transformer in the middle. I know it's not really easy to see. We'll take a closer look at that in a second. But I really think that what's blowing the horizontal output transistor, which is this component right here, is either a bad flyback or a bad deflection yoke. One of these two parts is probably bad. And what that means is inside of this, instead of the coil just being a nice continuous loop and coming out of the two pins, something is shorted inside of this, either a diode, because there are diodes in here, or the coil itself has shorted turns, meaning instead of it just looping it over and over again like hundreds of times, if the insulation breaks down, it can actually cause a short, and that loop, that inductance, is wrong. And what a ring tester does, I think I'm going to butcher this because I don't fully understand, but I'm pretty sure what a ring tester does is it sends a pulse into something like a coil, like this. And what that pulse does is when the coil is working properly, is it rings. It goes back and forth as it oscillates, and there's resistance to the coil itself, right? So it actually dissipates. So when you take a look on the oscilloscope and you hook it up while you do this test, is you see a pulse, and then it just keeps going like this, and it gets less and less and less and less until it fades to zero. And this thing will count how many rings there are. That's how many oscillations there are before it reaches a specific threshold, which, you know, is determined inside of this device. From the best of my understanding, when there are shorted turns on a coil, like inside the flyback or inside the deflection yoke, that pulse gets absorbed very quickly by that shorted turn. So that loop that's now shorting instead of it being a continuous loop. So instead of seeing a good, nice pulse that just slowly decays, and we'll be able to look at that on the oscilloscope in a second, you see the pulse and then it very quickly decays down to nothing. So first step is I need to take this set apart and I need to extract the flyback. You need to take it off the board to do this testing, this ring testing. For the deflection yoke, I don't need to remove from the CRT, I just need to unplug it from the main board, and then we can test, comparing to these, the rings and the inductance. Now I will throw something out there. This deflection yoke is totally different than the one that's on this. It's not from a similar set. It's just from another 13-inch set. So the values we're going to see on here are not going to be the same when it comes to the inductance or the rings. And the same for the flyback, because I don't think these are the same parts, even though they have the same footprint. I should be able to tell, based on the schematic, where the primary and the secondary coils are inside the flyback, because they're just depicted on here along with the pin numbers. So I should be able to ring out the primary and the secondary side of this flyback, which, you know, is working, like I said, and maybe it's not going to be exactly the same, but we should get an idea for the rings and compare it to what's in the set. Ideally, you'd want to have two identical flybacks, one that works out of a working set and one that doesn't. And then you could compare and try to identify where the fault might lie. And the same goes for the deflection yoke. You want to compare like for like, That way you can know, okay, the readings should be this, and on the bad one or potentially bad ones, they are this. But if we compare the rings and the inductance between these 4 components, even though they're not identical, but I'm thinking there should be close enough, maybe we can get an idea that perhaps the fault does not lie in the flyback or deflection yoke. And these are 2 parts, especially the flyback, that are unobtainable. If the flyback is bad on this set, that is the end of this repair. There's no way for me to get a replacement flyback. I could try putting this in, but it could easily just blow something else up in the set because these windings, and if we go back to the schematic, I know it's going to be hard to see. The primary, which is the horizontal output transistor, this section right here, drives these coils right there. Well, there are secondary coils there that generate the high voltage to go to the CRT, plus there are these there, and they move over to here, and they generate some auxiliary voltages that go to, I don't know, other parts of the set, like 8 volts, and there's the filament voltage and things like that. So these have to all be the same, and it all depends on how many turns and the way the flyback is built inside. If I put that other flyback in, the pinout's the same, but say the number of windings inside are different, when the set operates, the secondary voltage coming out of the high voltage anode, instead of being like 24,000 volts or whatever it's supposed to be on this TV, could be 30,000 volts, could be 8,000 volts. And then also these other windings that come out that go to various voltage rails, well, instead of 6 volts going to the CRT filament, we might be getting 30 volts, and that would destroy the CRT. So it's hard to know, and I just don't know enough about how these flybacks work, if there'd be a way to even measure that to know what the primary, secondary turns are and the ratios and all that stuff. There's a lot of magic going on inside of there. That's why if all else fails, I guess I could put this in and so what, it blows up the rest of the TV. But I would like to not destroy or damage the CRT because that probably works and it will be usable in something else. Anyhow, so that's the general plan for this video. So first things first, I'm going to open this up. It's just taped together right now, and I'm going to pop out the flyback. That should be pretty quick and easy. And I'll disconnect the deflection yoke so we can start some testing. So this is the TV that's under test, and I've removed the flyback. Now, one of the things I mentioned before is it seems like the pins that are connected and not connected are different on this one than on the parts board. So for instance, 1 is connected, 2 is connected, 3 is connected there, 4 there, 5 seems to not be connected to anything at all. 6 is connected down here. You can't really see it, it's off camera. 7 is connected somewhere down there. I can see the trace going around and down there. 7 is connected down there. You can't really see it. 8 also goes down there. 9 goes down there. And 10, is this actually connected? It's kind of messy on the board. Is this connected to this ground here? Let's see. Yeah, pin 10 looks like it goes to this ground flood fill, which makes its way over there. So the only pin that's not connected over here is pin 5. Now on the parts board, things are different. Pins 1, 2 are connected, 3's not, 4, 5 are connected, 6 is not, 7, 8, 9, 10 are connected. So 3 and 6 are not connected on this board at all. And that really sort of reinforces the fact that the flybacks are not interchangeable. Even though the footprint is completely the same, the fact that this stuff is all different leads me to believe that things are quite different. Now, when it comes to the primary and the primary always being the high voltage side connected to the horizontal output transistor. Pins 1 and 2, definitely the primary. One of them is going to be going to B+, I think, and the rest of the deflection circuit. And then the collector, the output of the horizontal output transistor, which is the collector, is down here. That makes its way, it looks like, to pin 1. On the board I'm trying to fix, pins 1 and 2, they are also the primary. Down here is the primary, so that's the collector of the horizontal output transistor. That makes its way, to that stuff. And then that's probably B+, this one that's circled. And I think that was from when I was testing to see if the B+ was shorted or not, part 1. That's why that's circled. So at least that's very similar. All of this stuff here is going to be secondary, generating those other voltages like the filament voltage and whatever. It's going to be all of those. But on the one we're trying to fix here, pin 3, definitely is connected to something. It looks like a coil, and it goes off to somewhere else. And just to remind you, pin 3 on the test or a parts board is not connected to anything at all. So that's not super reassuring. So things are a little bit different between the two flybacks. But like I said earlier, I'm just hoping to get a good general feel for the number of rings that we should be seeing on the working flyback versus the one that I just removed from this board, which is this one here, and I have an X on it. That was from before, just so I can tell them apart. And just so everyone knows, there are the 2 part numbers side by side. So both JF0501s, but this one's a 19304 and this was a 19105. But this middle line, 37-05-0119-10503 versus 37-51192-55ROX. So quite different, but they look physically identical. But I'm just assuming inside, they're not. So first things first, what I'm going to do is I'm going to use my LCR meter, that's this yellow one, and I'm going to measure the inductance of the deflection coil, both the horizontal and vertical on both of these. And then I'm going to do the same on the primary plus all these secondary pins on both of the flybacks. And I'll write that all down so we can just sort of compare the two. And then I'll start doing the ring testing and we'll see if we can see the fault with this component or that component. All right, this is what I've come up with. So these are the inductance measurements for horizontal and vertical on the deflection yoke from the part set, 3.9 millihenries, 26.7 millihenries as well. And from the Phillips set that I'm trying to repair, it's 2.0 and 33.6. So these aren't close enough to really be compatible. I have a feeling if I tried to swap these deflection yokes, there would be deflection or geometry issues, so to speak. Just showing though that the measurements are still normal-ish. Usually, or almost always actually, the horizontal is going to be a much smaller number than the vertical. So this is pretty typical. Oh, and if you're looking at one of these and you're trying to figure out which is which, a lot of times there is some heat shrink on top of the horizontal deflection coils, and that's because it's much higher voltage and they don't want you to accidentally touch one of these while the set is running. So I had to cut the heat shrink off of these. Now this coil that goes down around here, it's connected to these two pins on both sides. That is going to be the horizontal deflection. All of this stuff, as far as I'm aware, is going to be the vertical. And if you look at this deflection yoke, which is from I don't remember what brand TV this is from, but it wasn't even a Phillips. You can see that there is a gap in the connector, and that's very typical to be the horizontal deflection. That's because, as I said, it's higher voltage, and they want to keep those apart. So if we look at these two pins, we have a red wire, and we have a blue wire. The red and the blue have a gap between them, and then these two are right next to each other. So these two, the yellow and the brown, that's going to be the vertical deflection going to these larger coils, and these ones are going to be horizontal. So that's how you can kind of tell them apart if you're trying to use a tool to measure it. And by tool, I'm using this LCR meter, but you can get all sorts of these now inexpensively. Something like a multimeter, incidentally, like this one here, this cannot measure the inductance. This doesn't have that capability, and it's not common for multimeters to have that ability. It looks like everything is okay here. I had measured this before, like in the previous parts, and that is exactly what I got before. And this seems correct to me. I've seen plenty of deflection yokes on parts TVs that have inductance that look just like this, so I'm not suspecting anything's wrong. We'll still try to ring test this in a second just to see if maybe there's an issue with one of these. And remember, by the way, just incidentally, all we're concerned about with this set is a problem in the horizontal circuit. Things that are wrong in the vertical circuit, like in this side, that's not going to cause any issues here. This is a separate system where the horizontal output transistor is blowing. So we have to worry about just the horizontal side. Vertical is irrelevant. I mean, it's relevant from a compatibility standpoint if you're going to try to use this yoke on this set. But in this situation, we're only looking to the horizontal. These are the measurements that I got on these two flybacks. This one here is the parts set flyback. This is the one from the TV that I just removed. I know it's going to be a little bit hard to kind of see what I've written on here, but one thing I can tell you 100% for sure is that these flybacks are completely not compatible with each other. When we take a look at this again, this is the primary, pins 1, 2, and 7, with 7 being a center tap between that coil there. And it looks like that has the effect of, I think that means it's generating the 160 volts. B plus on this set is 96 volts or something like that while the set is operating. That comes from the main power supply. Let's see, is that this right here? Yep, that's it. So the arrow is pointing in, which is saying that signal is coming into the coil. And then what's happening is, remember, the horizontal output transistor, when it is conducting, so the base is turned it on, that is connecting this entire thing to ground. There's the ground connection, and it loops around through this to the 95 volts. So from my understanding, while this is conducting down to ground, that's charging up this coil. This is charging it with this 95 volts. And then this opens, and that causes the field to collapse. And I think that puts the current and voltage and stuff into these other secondary coils there and there. Now going back to the pinout and the inductance on this flyback, remember it's 1, 7, and 2, which are the primaries. And that pretty much matches the Phillips here. So between 1 and 2, we get 2.0 millihenries. And remember, pin 7 was that center tap, and we're getting 17.0 or 1710 microhenries to pin 2, and we're getting 1480 to pin 1. So if we go back to here again, pin 7 looks like it's kind of in the middle, but you notice like there's a longer coil on pin 1 to 7 versus 7 to 2. We go back to here, 1 to 7, 1480. 2 to 7 is 1710. So I don't think that the way this schematic looks necessarily is relevant to the way this looks, but at least it shows that 7, 1, and 2 are all connected together, and we have inductance happening there. The rest of the pins, on the other hand, 9, 10, 6, 5, 4, 3, these are all sort of connected together, and I get all sorts of different readings here, and it's all a little bit of a scribble, but it just shows that there's definitely inductance happening between all the rest of these pins. And that makes sense because look, 6, 9, 10, 3, those are all connected together. Then there's a little point that comes off here, goes down to 4, goes down to 5. There's also a trace that goes over here, and it makes its way over to this, which EHT, that's the high voltage that goes to the CRT. And then we also have pin 8, which is going through an internal diode, and there's also some other diodes inside there. And actually, you can see that these are the two potentiometers right there for the screen and the focus control, which go off to the CRT as well. Point being is, I don't think you can really measure the inductance between pin 8 because it's going through a diode right there and a coil internally, and then it's going through these two potentiometers, and it does make its way back over to these pins. But that's pretty much what I wrote on here. Pin 8, I couldn't really measure it. I meant to write EHT, it looks like a G, but it's an EHT. So you can't really measure that one. But all these other pins seem to be connected and seem to have some inductance stuff on them. Oh, except for pin 5, which I think matches here. Okay, so pin 5 actually is connected. It just, I don't think it actually goes to anything on the board. So I didn't bother measuring it. Oh, I did, 9.7 millihenries or microhenries. U is a micro. Anyways, point being is if we compare it to this other flyback, well, this is very different. Really, there's only connections on the primary side between pins 1 and 2. All the rest of these pins seem to be connected together, and lots of millihenry measurements. I think pin 6 on the other flyback doesn't seem to go to anything. It seems 100% open, which makes sense because the PCB on the spare board had nothing connected there. I think pin 10 also might not be going to anything. It looks like it goes to something on the PCB, but it's like a spark gap or something like that. So I'm not 100% sure what's happening there. But point being, it's very clearly, these are different. Pin 7, which is absolutely connected on the primary side, while on this thing, it's all connected up to these other pins. So if I had tried to use this flyback in this board, even though it fit, I think really bad things might have happened. So I'm glad I never turned it on. I think it was in part 1 that I had this one installed in this board, because clearly these are not compatible. But what we can do here is we know on the primary side, 1.77 millihenries is, close-ish to this 2.01. So we should be able to do this ring testing on the primary side, and then maybe we can do the ring testing on some of these other pairs of pins on here, just to kind of see if anything looks out of the ordinary. If I had the schematics for the other set where that parts flyback came out of, then, we'd have a better accurate description of like the way it was wired internally. But clearly, by the way, I see a part number AT2078. That's interesting because that doesn't match at all. Let me find the right flyback. This is the one that's that one. Is that number even on here at all? No. 2078? I mean, how funny is that? Oh wait, I just noticed another number, but that also doesn't match. Huh. And this is the parts flyback 10609B. That's the same. But then this says 55205UG, and this one's 3403G. I don't know. I bet there's people watching who might know more about these types of things, like these part numbers. Help me understand what these numbers mean, and it's pretty hilarious. Yeah, we're looking at the schematic. I think I looked at the parts list. It had the number that it didn't really see on either of these either. It's just confusing. It's very confusing. All right, we're gonna be using the Sencor to do this ring testing now that I have some measurements done, and I'm gonna be using this oscilloscope just to look at the waveform that this generates so we can try to see if there is any kind of issues with the pattern that this generates. This is the oscillation I mentioned before. It'll make sense once you actually see what's coming out of this when it's hooked up to some of these devices. I have the oscilloscope set to normal trigger mode. That means only when it triggers will it draw a waveform, so that way when I release the test button, the ringing test button, then this will actually keep the waveform displayed. First, let's start with the horizontal deflection on this yoke. So these leads right here, they go to the input on this device. And I have it connected up to the horizontal deflection. And remember, you gotta do this out of circuit, so we have to unplug this. Of course, it's not plugged into anything, so that can't work. And let's just give this a test. So I'm gonna hold down the ring test button, and it says 15 rings. Now there's an adjustment here that you're supposed to match the inductance value, so I can hit the value button, and it's saying that it's measuring at 4 millihenries. So let's turn the knob up 1 notch there and push the button again. Now it's saying 22 rings. And if we turn this up 1 more, let's see, 22 rings. Okay, so that's about right. There's no scale written on this knob here. You're just supposed to do impedance match. I can see down here 10 microhenries and over here 1 henry. And we're at, what, 4 millihenry. So it's somewhere in the middle. So there we go, 22 rings. Now what does 22 rings mean? Let's hook up the oscilloscope. All right, so the oscilloscope is hooked up. I'm gonna hit ring test. And there's a waveform is being displayed. So we got to change the time base though. So hopefully that's in focus. Essentially what's happening is a pulse is generated by the send core and then it rings, it oscillates back and forth in this coil, but it slowly degrades. So it sends just 1 pulse. The first initial pulse is there. In fact, what we can do to test this, I'm just going to connect the output of the send core directly to the oscilloscope without the deflection yoke being hooked up. And let's hit ring test. And there you go. You just see 1 waveform, it goes up and it slowly degrades. So there's no ringing that's happening right now. And of course, when I hold this down, it just shows 0 because we're not hooked up to the coil anymore. But hooking the scope probes back up, I hit ring test. There we go. So what the meter is doing is it's counting the number of oscillations that are happening. And it's showing, what, 21, 22. And I think there's a cutoff because we can see it keeps going over here, and I think that's more than the 22, but I bet you it cuts off at some particular value. It's all a bunch of magic stuff. I think people will understand better what this means, but from what I understand is if there's a problem in the yoke, like a shorted turn, then instead of it going for a long time, it'll maybe have like a couple pulses and then quickly go to 0. And this is what we're looking for. We're looking for a good waveform like this on all the stuff that we ring test here. So time to move over to the other deflection yoke because we need to make sure that the horizontal deflection on the set itself is similar to that. All right, it's all hooked up. And remember, this is unplugged. And this one here, this is the horizontal, which is what we care about. So we're ready to test this yoke. All right, we're getting 15 rings. I mean, I think that still looks like a good waveform. Let's go one further. All right, now we're getting 21. What's the deflection yoke's inductance? Let's take a look at the little sheet that I have here. So according to my sheet, the parts set actually had a higher inductance, around 4 millihenries, and this one's only 2. What does that do when it comes to what the waveform looks like on the ring test? Well, I don't know exactly. Obviously, I have the knob set 1 higher than I had it on the other one, and we're getting 21 rings, but if we lower this down, it certainly shortens the pattern. We have to zoom in here to look at it, but I think it still looks good. It's like a nice decay. I'm not really seeing any kind of issues there. I don't know. Is that good? Bad? Who knows? But I'll just write it down on this paper because I just don't know, but I think that looks okay. So fiddling with the adjustment knobs, I got 22 rings on the parts yoke. That's this one here. And on the actual TV, I got 21 rings. I don't know if that's good or not, but at least the waveforms look similar. Let's switch over to the flyback. Now I'm going to go on the primary side between pins 1 and 2. By the way, I also tested this ring testing with the oscilloscope disconnected. It doesn't really seem to change anything on the value. So let's see what we get on this thing. So what is the primary? 2 millihenries. Actually very similar to the inductance on the yoke on the TV. Which one are we testing here? Oh, we're testing the parts one. 1.7 millihenries. Okay, well, let's see what this gives us. Oh, I can hit value, 1.84. So it measures a slightly different than my LCR meter, but it's probably a different frequency that it's using or something like that. So whatever, close enough. Let's try this. All right, 73 rings. Let's turn this down. When we zoom in, we can really see that there's a long decay for this. So it's showing 65 rings right now. And this is the parts flyback, the one I know works well. And I mean, look at that. It's going on and on and on and on for quite a while. Now, if we switch the knob and I push it without changing the time base, now it's even longer. We're at 73 rings indicated, but I think that might be a bit too high. 38 is probably a bit more realistic. 60 kilohertz, the frequency. It's a little high though, compared to what this actually operates at, but who knows? There we go. We're getting a waveform, 38 rings. So we're getting 31 to 65 rings, depending on the setting on the knob here. This is with this parts flyback. Okay, this is the flyback from the TV, the one we're trying to fix. And we're on the primary again. Here we go, ring test. I mean, it seems fine. It's interesting how it kind of got more and more, but we're at 41 rings, and I think we're on the same setting that on the other one I was getting 31. Well, that certainly doesn't look like any kind of problematic ring pattern, does it? I don't think. I mean, unless the voltage is lower. The amplitude seems a little bit lower, but the inductance is lower, and it's clearly a different flyback. But I don't see any kind of thing that looks like maybe a short or something like that either. Let's just give a test here. I have this resistor. Let's hook a resistor up between those two pins. There we go, totally dead. So we get like one oscillation and then that's it. Let's see if I fiddle with the knob, if we even get one ring out of it. Now we're getting 0 rings out of it. Okay, we're getting 1 ring out of it here, but see how quickly the waveform just sort of dies? So I think that's sort of indicative of what a shorted turn is. Actually creates a little short circuit inside and it will actually pretty much decimate the waveform very, very quickly. But everything on the primary side here looks like it's working. So remember that this flyback, the one on this TV, actually pin 7 is also related. And sure enough, yeah, I mean, look at that. Let me turn this down a little bit. So we're getting plenty of rings out of this connection from pin 1 to pin 7. So that seems good to me. And I just switched to pin 2. So pin 2 to pin 7. So that this waveform here is just because the time base is incorrect. See, if I zoom in a little bit, now we're seeing a better waveform. So is this a bad ring test waveform? I don't know. It looks fine to me. I just don't see it dropping off super fast. It seems to oscillate and go on for quite a while, as we would expect. It really, really does. So primary side on this flyback, in my opinion, which is very limited and I don't really know what I'm talking about, it seems fine. Now I suppose what I should do is maybe do some of the secondary stuff and just look at these waveforms. And so I'm going to do that off camera because it's probably all going to look the same, and I'll come back if anything looks weird. And I'll do the same on the other flyback, the parts flyback. Okay, I just went through all the pins and everything looks fine. I don't see any issues. This is the flyback that's off this set. It all looks perfect. Unless there's a problem with a shorted diode or something inside of here, I don't think there's necessarily a problem with this flyback. And on the parts flyback, everything is pretty much the same as well. I mean, based on the pinout that I have here, I'd say that these are absolutely, like I said, not compatible, because that primary pin 7 is definitely connected to the secondary on this other flyback. But all of this stuff pretty much rings out 40, 50 rings, and the waveforms look good as well. So yeah, okay. Well, that's good, because that seems to indicate that there's not a problem with this flyback. And there's not a problem, well, not with this flyback or yoke, but the yoke that's on the set. Everything rings out and the waveforms look good, which kind of leads me to believe that the fault on this set is something else. There's got to be like a shorted diode or something. So I think what I need to do now is take the schematic, which I now have, and look at all the diodes that are on the secondary side and look for anything that's shorted. If I don't find anything that's shorted on the secondary side, like every diode is perfect, and the flyback looks fine on all this testing, and the yoke looks fine, I'm honestly at a loss. But before I say I'm at a loss, let me just go through with the multimeter here and check for every single diode that's on this horizontal circuit on the secondary side, and we'll see if anything looks shorted. Talking to some technicians after I posted the last video, yes, theoretically, if there's a short on one of these secondary rails, it could potentially cause this problem, because this horizontal output transistor has to switch and pass current to charge up the flyback, which then is powering up all this stuff. Well, if something is drawing too much current here, maybe that would cause it to fail, because it would be passing too much current, potentially. Again, this is all like this magnetics and magical stuff, and I'm not getting really clear answers from people. They're just saying, yeah, it's possible it's this or that or this or that. There's a whole lot of possibilities. But certainly when it comes to why the horizontal output transistor is blowing, like we've had 2 blow now, yeah, no concrete answers. All right, I've been spending a bunch of time going through all of the semiconductors, which are all the diodes. This is all on the secondary side, everything on the primary side, stuff up here. Everything seems fine. I've even gone ahead and checked some of these big resistors just to make sure that they are looking good. And I'm really struggling here. I am struggling to find anything that looks wrong. One thing that's odd is I can't find 6705. I've looked everywhere. Now what's annoying is this has a little thing here, lists all the parts, tells you where on this schematic it is, which is helpful if you're looking at the actual board itself. If you're looking at this, you find a part and you know it's in the horizontal section. Well, you can just look it up and you're like, oh, there we go. It's a A7, you know, whatever. It tells you where to look. What's really frustrating is there is no equivalent little chart here showing you where to look when you're looking at this. This is a top-down view, and I was looking for 6705. There's the flyback. Horizontal stuff is all going to be in this area. So like 6704. Where is 6705? I've looked everywhere here and I don't see it. And there's no chart to tell me where to look. It's probably here and someone probably spots it right now. The only thing I can see is 6750, which I wonder if it's a typo. 6705 is actually 6750, but it's quite possible that 6750 is part of the vertical section. Let's scroll to vertical. Yeah, frame deflection. This is the vertical deflection. Do we say 6750 on here? Yes, we do. Yeah, A2, 6750. Okay, so that is not a typo. That particular diode, there it is there, 6750. That is for the vertical, which is kind of what I assumed. But 6705, which is the same diode type as 6701, is BYD33D. I just don't see it. There we have 6700 right there. 6704, there's 6701, and the package that's actually on the board is just a little tiny glass, kind of orangey red color diode, the same as all the other ones. So we're looking for 6705. Just scream when you see it. Scream when you see it. So there's 6701. We're looking for 6705. It's going to be the same package as that. Let's look on the back side. We know 6701 and 6705 connect to each other on the band side. So if this would focus, there's a trace that would go on that side to wherever that other diode is. Okay, 6701, the band, well, that doesn't go anywhere. It just goes right to that 0 ohm jumper link, another jumper link, another jumper link. Looks like it goes to that, like it makes its way there, up here. Ah, there it is, 6705. Wow, it's so far away from the vertical, or the horizontal. I just wanted to see if this thing has a correct diode drop. Yeah, it does. So that was really the last one that I hadn't checked, and that diode is good as well. Well, let's check this resistor here, 3705. Okay, so 3705 is right there. I think that is actually this part, there to there. I know it's hard to tell, but this is a really big diode, and I already checked it on the other side, but just switch my multimeter into resistance mode. And we'll go from here to here. We're at 100 ohms, 220 ohms. Okay, but it has an asterisk there. I bet you this is a part that's different depending on the set. So we got to look at the parts list for 3705 for this particular TV. I mean, the reality is that I'm sure this is completely fine, and that's because, you know, it's not open. If it were open or something, then I would be suspicious. All right, so 3705, let's see what TV this is for. Yeah, 13MT 1432. I gotta look at the back of the TV, but I'm pretty sure that's what it is. It says 100 ohms, metal film. Actually, this is a 13MT 143. 13MT 143, there we go. Yeah, okay, same thing. It's still 100 ohm metal film. I'm quite sure, again, the asterisk means that this value changes depending on which model of television it is. So for different model, it might have a 220 ohm resistor, but it has 100 ohm in this case, and it does. But generally with these resistors, what you want to do is just check the board. You don't need to necessarily look up the value. The fact is it's 100 ohms, that's, you know, that's a precise value. If it was something weird like 3.98K or something, and it was a large power resistor, let me show you exactly what I'm talking about. These types of resistors here, these large metal films. So that one there, that one there. In fact, one of these is going to be our part. I think it's this one right here, 3705. Yeah, so that's the one. And obviously, if you can read those values by the color codes, then you'll know what it is. But I mean, I measured 100 ohms. That's not burned. It looks fine. So I'm not suspecting any issues. I also checked these ones over here. It's possible this one here is for the vertical. That's the vertical section. But this one is almost certainly related. That one's fine. Those are fine. This one over here is fine. I mean, everything is fine. I even started checking these parts here, looking for shorts, for instance, across these caps, all of this stuff here in the horizontal, and everything seems completely fine. I'm not seeing any issues whatsoever. So as I sort of suspected earlier, but I didn't want to jump to conclusions, I'm at a loss. I have no idea what's wrong with this set. No idea at all. Ring testing with the Sencore, things looked fine. I think people who know more about this can look at those waveforms I was seeing on the oscilloscope and maybe point one out that seemed wrong. But having gone through all the stuff here on the horizontal, I just don't really know. Someone suspected that they thought this problem existed on the drive side. So that would be the horizontal output signal that went through that small transformer. And remember, I swapped out the transformer from the other set, which might have contributed to the fact that it blew the horizontal output transistor very quickly. But even when I tried the spare horizontal output transistor in this before I swapped out that transformer, remember, it overheated and the set didn't run. So it wasn't like it was running. But this here is the drive side. So this is the transistor that's driving the transformer that then drives the horizontal output transistor, which then drives the flyback and the deflection yoke. Maybe I need to find this transistor on the board. Maybe this is somehow problematic. The drive signature itself looked okay. Unfortunately, the voltages we see here, see 9.2 volts, that's while the set is operating. It doesn't show us on here what the waveform should necessarily look like going on to the drive side, the primary side of the small transformer. Although, oh, you know what, let's look at the, there's a section in the schematic with waveforms. And we'll look at that in a second, but see how it says L1, L2, L3? These are waveform pictures that it actually has. So it will show us a picture of the waveform coming from the IC. Unfortunately, it does not show us a picture of the waveform on this side of the transformer, the primary side of the transformer, which is annoying because this is exactly what we need to see. They just seem to have a waveform of the base drive, and then the collector side of the output, horizontal output transistor. So here are these waveforms. Okay, so I'm looking at the schematic. I know you can't see it. L1, this is the base drive that goes into the drive transistor that drives the primary side of that little transformer. So we should be seeing like a 15 kilohertz signal that comes out of the main chip. 200 millivolts per division, so it's pretty low voltage. And then L2, this is the base drive that goes to the horizontal output transistor. Now you see these large spikes here, and it's 5 volts per division, so the spikes are, 15 volts going negative. I think that is specifically generated by, if we look at L3, this is the horizontal drive on the collector side. So L3, this is 400 volts per division. So we're looking from here. Imagine this is going to be, maybe 900 volts, something like that. These spikes, I think this is generated by all the magnetics that are happening, like the collapsing field in the flyback and the deflection yoke. And I think that's what's creating these spikes. So basically the waveform is, it goes from here up to there, and that's like charging. And then I suppose it disappears, the drive signature, probably when this drops down to ground. And then when that happens, this all collapses and you get this big spike. Well, and you get that big spike, and I think that's what's generating this spike. We did not see this. We also didn't see this big spike. We were only getting maybe 200 volts on this side, and we really didn't have this large spike on the base drive going to the horizontal output transistor. But I'm assuming these things are related, and this is while it's operating normally. And then as for the drive signature coming from the chip, I mean, it pretty much looked like this from my recollection, pretty low voltage. I mean, we just have to kind of imagine that this is turning this on and off, so this particular waveform should look similar to what this looks like. Maybe just the voltage is going to be a little bit different because, see, it's connected to this 25 volts, and according to this, it's 20 volts or 9 volts while it's running, so it should be swinging 9 volts down to ground or something like that. So maybe it's worth us looking at this again. Of course, this part is out of the board, but the resistor here, this 47 ohm resistor is still there. So there's still gonna be some load on this side, even with that part removed. So like I said, we're not gonna see that big spike happening as this thing is switching because all the magnetics are not there. Yeah, I'm just not sure. I think I'm gonna look at this part here, 7700. Let's find that, see what kind of part this is. Right, here's horizontal drive. There's the transistor right there. Does it say 7700? Yes, it does, right there. Maybe that's somehow damaged. I'm really at a loss here. Why don't I just remove that from the board and we'll test it out of circuit. And while I'm at it, I'm going to remove this little transformer. I'll put back in the original one. All right, there's that little transformer that I put in. It's going to be hard to see, but there's that little transistor down there. Let's grab that, pop it out. C33725, whatever that is. HFE is 331, 2.1 milliamps, and 620 millivolts for the UBE. These are the values. The 331 is the HFE, and according to the data sheet, the HFE on this, the 337-25, should be between 160 and 400. There's no typical value stated. And then the VBE-based emitter on voltage, the max specified for the data sheet is 1.2 volts, and we're at 620 millivolts, which I assume is okay because it's smaller, which just kind of leads me to believe that there's actually nothing wrong with this part at all. Let's check that there's this 1K resistor in place, 3710. That needs to be there for this to work properly. According to this, it's about 1K. It's just slightly off 1K. And according to this, 1K. So that's fine. Then we have a little resistor, that's a 0 ohm. I don't know, not seeing any problems in this circuit either. I think what I'm going to do now is I'm just going to put back this transistor, the original transformer, and I think I found a suitable horizontal output transistor. So I'm going to refit those parts. So I decided to take a quick look at the troubleshooting in the service manual just for the flow charts. I always found them to be very useless, but just so everyone knows, this is the main power supply. So main supply, 97 volts. I think that's maybe with the set not running. There's also a main aux output, 11 volts. Those are the two voltages that the power supply generates. And if we scroll up to the troubleshooting flow charts, I just sort of took a quick look at this. It's kind of useless, but I guess it's something. So introduction, is there approximately 165 volts on pin 1? This is the DC voltage before it goes through the power supply. No point to even check that because how many secondary voltages are present? And all present. So what I didn't check is that we know we have the 97 volts, right? That's a B+. We don't know if that 11 volts is there, but I'm pretty sure it is because the whole set tries to operate, right? If all are present, we go to A. I suppose I should probably check that in a second, but let's just look to the A part of this troubleshooting flowchart. Here it is. Does a momentary horizontal pulse appear on pin 7 of the IC7000? That's the horizontal output signal we've been looking at. Well, we know that it has a signal. So yes, go to C. No, it's wanting you to check other stuff. Well, we don't need to check this other stuff because we know that that's being generated when you try to turn on the set. It's funny that it says momentary horizontal pulse. I don't know why it says momentary. It's not, there's more than one pulse. It's just running at whatever, 16.7 kilohertz. Anyways, we go to C. So let's find C. B, here it is, C. Is there a horizontal pulse at the base of 7700? Well, we know that happens to be the drive transistor, the one I just checked. That's the one that drives the transformer. Well, we know that there's a signal there, so yes. Is there a momentary pulse at the base of 7701? That's the horizontal output transistor. We know that's a yes. Like it's telling you to try these things if there's a no. Well, we know that it is generating, there is a pulse. And is there a horizontal pulse on the collector of 7701 when the power button goes? Well, yes. It doesn't look fully right, but it's there. And does the collector voltage on 7721 go low when the power button is pushed? Well, what 7721 is, the collector voltage. Let me go show you where that is on the schematic. Or actually, I can just show you on the printout. That's this transistor right here. So the collector is coming from VLOT 8 volts. Well, VLOT 8 volts is generated by the flyback itself, right, from this rail. Well, we didn't check to make sure that was working because the whole flyback wasn't really generating. I mean, we didn't see the normal switching pulses from the flyback, so I didn't even bother to even look at those. But this is what I think turns on and activates the filament voltage. Right there's the filament, right? There's no point to really even check that because we know the issue is seemingly existing up here. Well, if we look at yes, because I'm pretty sure we do have those voltages, and we're looking at the dead set troubleshooting, by the way, it says suspect the timing capacitors, a collector circuit of 7701 or the flyback transformer itself. That's it. That's the end of that troubleshooting. No, it kind of goes on to a bunch of other stuff. And if we go over here, we say, no, we've determined that the set is being held off by any of the protection circuits. Well, That's clearly not happening. Yeah, there's a bunch of protection stuff in this circuit, and if it doesn't detect what it wants, it will immediately shut down. And it does look like the set did shut down. I mean, it blew out the horizontal output transistor, but before it did that, it would kind of run for a little bit, and then it would turn off, and that was a shutdown state that it would go into. But it would run for several seconds before it would go into that shutdown state, and it still managed to blow the horizontal output transistor before it went to that shutdown state. Well, there are these protection takeoffs of these secondaries for the flyback, and it does measure those. So I guess what it was unhappy with is that it expects those voltages to come up and stabilize, and they weren't, which is why it was shutting down the set. But it wasn't doing it quickly enough to prevent blowing of the horizontal output transistor. So once again, I'm completely stumped. This flowchart was completely useless, which is what I kind of assumed it would be. I'm just thinking, like, what if the CRT itself is bad? What if the whole time the CRT itself has a short inside the CRT? You know what? For grins, I'm going to go grab the CRT tester and I'm going to plug it into this set. And we're just going to check to make sure that this CRT is actually good and doesn't have any internal shorts. Because that would be hilarious if it did. I don't know how internal shorts in the CRT can blow the horizontal output transistor, but maybe in this set design, it operates so on the limit, the horizontal output transistor, that the extra load of the shorts inside the CRT causes the horizontal output transistor to fail. Now, the CRT is in phenomenal shape. No shorts between focus, the grids, or the cathodes. And if we take a look at the emissions test, it's very balanced. I don't know what it should be on this set, but it looks really good. The cutoff is really good. It's equal across all three of the cathodes. So yeah, nothing is wrong with this whatsoever. This is looking perfect. Based on what we saw in that troubleshooting flowchart, I should check that 11 volts coming from the high voltage power supply, and currently this is all turned off, by the way, is being generated correctly. Now, I happen to know, based on looking at the schematics, that this point here, which is labeled as P3, I think, this is going to be the B+. So I'll switch this over to DC volts, and I'm going to apply power to this board. Now, just a reminder that the horizontal output transistor is not installed. So everything else is installed, flyback and stuff like that. Nothing's currently connected to the set, but it's not possible for us to generate any high voltage with the horizontal output transistor missing from the board. So there's no danger of that. Of course, there's going to be mains voltages on here, so that's dangerous. So I don't want to touch anything here, but we'll turn on the set, and I just heard it start up. So we should have B+ right here. 96.49 volts, that sounds correct. So that's what we were just measuring there, P5, not P3, P5, sorry about that. Looks like main aux 11. We don't have a specific test point. See where P5 is, there's no similar point there. But if we follow this trace down to here, this is the optocoupler that provides feedback, and there's no power on this board right now, from the low voltage side over to the high voltage side here. This is the primary side, secondary side. So the optocoupler is right here, that's the location, and I'm looking for pin 1 specifically, which is going to be the top left pin. So that's where we should see our 10.8 volts, according to what the schematic says, when this is powered up. So I'm going to power up the set again. We'll just check that we have the B+ on the P5 point right here. 97 volts, so that looks correct. And let's check pin 1 of the optocoupler. 9.5. Interesting that it's slightly low. Now, according to the schematic, the top number, 10.8, is what it should be when the set's not running, and 9.4 should be what it is when the set is powered up. But the set's definitely not powered up right now, and it's at that lower voltage. Interesting. Let's see the other side of this optocoupler just for fun. Okay, so everything is live. So this is pin 1 again, so that should be 9.5, 9.6. That should be higher. And then this is the other side, 8.5 volts. And according to what I'm looking at, 8.4 is what it should be while the set is running. Very interesting that these voltages are a little bit lower than I would expect. But the B+ voltage, when we go onto that pin, 96.5 volts, which, if we look at the schematics, says 96, 96, and here, 96.4 while the set's not running, 96 while it is running. That's on pin 1 of the flyback transformer. So pin 1 of the flyback transformer is right here, 96.5. I mean, it's all pretty darn close. Pin 2, it said it's going to be 96, and it is, and then pin 7, 96, okay, because we know that pin 7, 1, and 2 are all on the primaries. So that all looks good. Now the collector of the horizontal output transistor should see also 96 volts while the set's not operating, and of course it's not even installed, so that is correct. You know what, I might have it backwards, that what's in the box, like 9.2 volts, is what happens when the set is not running, and 20 volts is while it is running. I realize here that this drive, this little transistor that drives the transformer, that drives horizontal output transistor, notice it has 2 voltages. Main aux, that's that 9, 10 volts that comes from the power supply, and then it has plus 25, and there's 2 diodes that feed this circuit. So the plus 25, you might be wondering what that is. Well, if we scroll over here, plus 25 is right here. It's one of the rails that gets generated by the flyback itself. So once the set actually starts running, it actually starts powering the entire switching circuit here with the 25 volts, which is probably why it shows 20 volts at the top. I think that's while the set's running, and 9.2 volts while it's not running. So let's check the collector on this transistor 7700. That's the one I took out and checked earlier in the video. Should be 9.2 volts right now. Okay, that collector there, 9.3 volts. Okay, cool. That's exactly what it says in the little box for that particular voltage. And when the set's running, that should be at 20 volts. So what we're seeing here is that all the voltage rails are looking perfect. I'm just gonna shut the power off to this board right now. Everything looks fine. The main power supply is definitely generating the B+, the aux voltage properly. The voltage that we should see on that transistor that's gonna drive the little transformer, that's gonna drive the horizontal output, that's all working perfectly as well. All the voltages that should be there for this set to work are there. Let's take a look again at the drive signature coming from this chip and what's going into that transformer, which it would be going to the base on the horizontal output transistor. I just want to look at those one more time, and we're going to see what those look like. And I'm going to currently use my 10x probe as opposed to the 100x probe I was using last time. So we'll have a little bit better of a picture of what those signals look like, just because I won't be dividing everything by 100. And since the horizontal output transistor is missing from this board, we're not going to have any high voltage pulses that could potentially damage this oscilloscope. And this is the little drive transformer that couples the horizontal output transistor to its drive transistor. And what I'm coupled onto, or what I'm plugged into, is the pin that's on the collector of the transistor that's driven from the main IC here. So when I turn this on, we should be seeing like 15 kilohertz, some kind of signal on there. So I'm going to apply power. Okay, so we are at 9.5 volts, just steady state on that transformer. And where's the power button? I think it's this button right here. There it is. There's our drive signature. Oh, and the set turned off. That's interesting. It went into protection mode. Well, that's not because something blew up. That's just simply because it wasn't getting what it was looking for. And yeah, I can't push the power button anymore. It wasn't seeing those voltages coming from the flyback, so we're going to have to cycle the power again. And it was going a little bit off scale for the oscilloscope. So I'm at 5 volts per division now. Let's turn this on, and let's turn on the set. Okay, there's our drive signature, and it turned off. So that was the set going into protection mode. If there was an LED on here that would flash to tell us there was a problem, it would be going right now, but we don't have an LED. So I'm going to have to cycle the power again. So let's just look at that one more time. Okay, so we're at about 10 volts. That's that collector current or voltage we saw before. And we'll turn on the set. There's our signature. And if I push the power button, it does turn off. Does I push the power button again? Oh, it turns back on. Okay, so because it didn't go into self-protection mode on its own, I can actually control this by trying to turn it off and on. So there's the set trying to run 15.7 kilohertz. And the waveform that we're seeing there is 18 volts peak to peak. That's what's going into that small transformer. Now I'm going to move the probe to the other side. Now remember, this is what's going to the base on the horizontal output transistor, which isn't installed in the board. So let's try turning this on now. It's a much lower voltage waveform, so let's just fix this. So just so everyone can see this, look at all the metrics here. So we have peak to peak, max, stuff like that. Turn this on. Let's see, I'll move this so it's a little bit more visible. It's sort of behind the, it's behind this little window here. There it is. 2.6 volts peak to peak, 15.7 kilohertz. This is me turning it off and on, by the way, since it will just go into its protection mode. So, I mean, does that look like a good waveform? 2.6 volts peak to peak. It actually looks like it's going negative as well. So max voltage is 1.4 volts on the positive side, because right now this is resting at 0 volts. That part of the transformer, when the set is off, is just not connected to any voltage rail, just connected to ground. So that's why we're not seeing anything there. And it's going up to 1.4 volts, and peak to peak is 2.6. So it's actually going negative as well. And when we look at these waveforms, this is the one that goes into the base on the initial switching transistor before the transformer. And this is what's coming out of the transformer that goes to the base on the horizontal output transistor. But again, we don't have it installed on the board, so we're not seeing these pulses. Of course, we're not seeing L3 or anything. So I think, I don't know, the waveform we're seeing there now, does that look correct? Does it not look correct? I think it should work. My assumption is the waveform that we're seeing there is correct for, well, when the part's not installed on the board. I have to just guess at least. And let's just look at that one more time. The set should still be okay. There it is. And if I just leave it, like I'm going to leave it here, it'll go into shutdown mode in a second. It should. Yep, there it goes. So now I cannot turn it on. Power button doesn't do anything. But if I turn the power off, turn the power back on, I can hear the B plus came back. Now I can turn it back on. All right, so that pretty much confirms, I'll just shut the power off to this. That pretty much confirms, I mean, all the signals really, really look correct to me. I just don't see anything that seems incorrect. Now, when it comes to trying this TV again, I found this scrap board, and this does have a horizontal output transistor. It's this part right here that has a compatible footprint, and it's the right size package and everything. So this might actually work. The one thing about this particular part though, is this component, I think this TV is a bit older. It hasn't, well, it's not really actually, I see 2002 date code, so it's 1 year older. That has an integrated damper diode. And the one on this set, plus the one I tried before that got destroyed, those don't have internal damper diodes. So those use an external diode, which when we take a look at the horizontal output transistor, which is right here, that is the damper diode. It is one I checked, it's that green mark, I checked that, and it's good. I mean, it's possible that that's somehow damaged. It tests good in circuit, like it has a right diode drop, but maybe it has a breakdown voltage. And that's what's driving down the output current. Because remember, when the field collapses, we should see that spike up to like 1,000 volts, and we're only seeing 200 volts. And maybe somehow that diode is causing that to happen. Let me just interrupt for a second. I want to talk a little bit more about this damper diode stuff. I didn't really understand this when I was working on the set. All I know is I looked up this part, the 2SD2627. This is specifically the horizontal output transistor that's in that scrap TV. And I noticed here it said on-chip damper diode. Now, what exactly is a damper diode? Well, we can scroll down here and we can see that in this diagram, there's the NPN transistor that's going from the collector to the emitter. The emitter always goes down to ground. Well, inside the package itself, it has this diode that's connected from the emitter to up to the collector. It also has a base bias resistor that's internal to the package. When we take a look at the transistor that was on this TV originally, the BUT11APX, this is just a normal NPN switching transistor, not really specifically for horizontal output duties. It just looks like a normal transistor, and inside the package it doesn't have any resistors, has no diodes in there. This is it. Well, it turns out on horizontal deflection circuits, and this is the schematic for this TV, you do need to have this damper diode installed, and that's it, 6704 BYD33M. This is the damper diode that's installed in the circuit because the BUT11APX does not have one internal. Obviously, Sanyo or whoever came up with this particular part, the 2627, they wanted to simplify the design of the TV, so they just integrated that damper diode directly into the component, maybe for cost-saving measures, not 100% sure. But it seems that this transistor, the BUT11APX that's on this TV, well, originally the one that was failed, and the one I replaced it with, which has a different part number, both of those require an external damper diode, which is this one there. Taking a look at the diode data sheet, the one that's on the TV is the BYD33M. It's a fast soft recovery rectifier diode, and it's good up to 1,000 volts, 1.3 amps. And we take a look here, the M variant, that is actually the one that is on the TV. There it is, 33M, or it's supposed to be at least. And that one is good for maximum repetitive peak reverse voltage of 1,000 volts, which should be in line with what's necessary for operation while this thing is switching and doing its thing with the horizontal output. Now we take a look at this line, minimum reverse avalanche breakdown voltage. I think this is the voltage where this thing can start to conduct. And on the M part, it is supposed to be 1,100 volts. Well, what if this part is somehow damaged? When I checked it with my multimeter, it still had a normal diode drop, so it's not shorted. It doesn't have that failure mode. But is it possible that these types of diodes get this problem where the avalanche breakdown voltage changes from 1,100 volts to, say, 300 volts? Could that explain what we were seeing before while the set was operating? The bigger question that I didn't fully understand, and you might not know either, is why is there even a damper diode on this circuit? Why is that even necessary? Well, I found this article by Sam Goldwasser. It looks like it comes from Electronics Now in March 1999, and it talks specifically about the horizontal deflection circuit on CRTs. Now we take a look at the circuit here, this example circuit. It looks pretty much exactly like it does on the set. We have the damper diode that's connected from ground up to the collector. There's a snubber capacitor. We have another S correction capacitor, and then the horizontal deflection yoke. On this particular diagram, B plus is up here at the top. It's connected to the flyback transformer, and then that's connected in series to the horizontal deflection yoke. On our TV we're working on, the damper diode is in exactly the same position. We have these two capacitors. One of them is going to be for snubber functionality. One is probably S correction. That has to do with the geometry, or sorry, linearity of the scanning. The one thing that's different on this set is that B plus is connected in parallel to the flyback transformer and the deflection coil, and that these are not in series like they are in this example circuit. And I've seen other TVs that are set up more in this way, but I don't know what the real difference is and why sometimes they're set up like they are here. Obviously, if the flyback transformer were missing altogether in this circuit, the horizontal deflection coil, if we're still connected, would actually be still connected through horizontal output transistor down to ground. So it could still potentially generate some kind of sweep, I guess, even without the flyback in place. It also goes without saying that if the horizontal deflection coil were missing or not connected, well, obviously the flyback transformer would still be getting voltage from the B plus, which would make its way in a loop like this down to the horizontal output transistor. Well, the question still is why do we have the damper diode? What is it actually doing? And if we took it out, what would actually happen? Well, it says here when Q1, which is the horizontal output transistor, turns off, that means it's no longer conducting. Since the current in the inductors, which is the two coils, cannot change instantaneously, the current is diverted into a snubber capacitor, C1. The inductance of the flyback and C1 form a resonant circuit so that the voltage climbs on C1 as the current goes down. At its peak, the voltage will be 1000 to 1500 volts. The snubber capacitor and C1 now begin to discharge in reverse through the primary of L1 until its voltage reaches zero. If there were no damper diode, that voltage would go negative and continue to oscillate in a damped sinusoid due to the resonant circuit formed by L1 and C1. Probably a lot like the ringing that we saw when we were doing the ring testing. However, D1 turns on as the voltage goes negative and diverts the current through it, clamping the voltage near zero. Note that in inexpensive or small screen TVs, the damper diode D1 may be built into the horizontal output transistor. That's also true for some monitors that don't have any circuitry for east-west correction. More on that later. Well, east-west correction has to do with like pin cushion stuff and external control, none of which is installed on this set because we know our circuit is very simple, kind of like this one. So the damper diode is preventing that oscillation and preventing this voltage from swinging negative. So it's a very critical part, and obviously it's very abused because it's constantly being turned on at 15.7 kilohertz and having to conduct a bunch of current through to prevent that negative swing. And maybe on this set, the damper diode might be damaged and is now clamping at a lower voltage than it should have been, 1100 volts. People who know more about electronics can maybe explain if that's even a possible failure mode for these diodes, that it could have that type of breakdown voltage change versus its original spec. And even if that were to happen, would that have any negative consequences in this circuit and specifically the horizontal output transistor? Just think about that as you watch the rest of the video and me doing the further troubleshooting on this TV. Okay, back to the video. So I'm kind of thinking maybe I should take out the damper diode. We could test it out of circuit, but I don't really have a way to test that properly because I don't have a high voltage power supply. I need to really put that on something very high voltage to make sure it doesn't have a breakdown voltage. But either way, I could take it out and I could replace the horizontal output transistor with the one from that other set without the damper diode. And we could just see what happens, see if it runs or see if it destroys that part as well. So you can see what I'm talking about. That's the horizontal output transistor. These are the two sides. So there's everything on this side. That's the deflection yoke connection, and that's the collector. And the damper diode is right there. It's in parallel with the deflection yoke connector. So there's the beefy damper diode. Doesn't look damaged. Looks completely, utterly perfect. So forward drop, 534 millivolts. I mean, like I said, I tested it in the board and it was totally fine. So I don't think this is necessarily bad unless it has a breakdown voltage that it shouldn't have. So in other words, like when those higher voltages happen, it starts to conduct when it shouldn't. Kind of like a Zener diode. Our part is a D2627. All right, and what's funny is it shows up as two parallel diodes. But I wonder if it's doing that specifically because it has that internal damper diode and you can't test it with these little testers. Okay, I'm just checking the pinout. It's not written on this board, but I can just look at it to figure that out. Okay, so that pin goes to ground. Yeah, pinout is definitely compatible on this set as it is on that other set for this part. So the horizontal output transistor is installed in the board. So theoretically, if everything is capable of running, that means that high voltage is possible with this set. So what I'm going to do is I'm going to run this without connecting the CRT. So this is the high voltage anode cap. It's in a glass, a thick glass, and out of way of other things. Obviously, we don't have the deflection yoke connected. I just want to run this very briefly for a second without it connected, see what happens. And I obviously don't have the CRT neck board connected either. And I'm going to bust out the 100X probe. So we'll switch this back to 100X mode. And I have the probe clipped onto the collector of the horizontal output transistor. And the oscilloscope will be set for 250 volts per division. Remember, the line there is the ground point. And I don't recommend doing this if you're ever working on CRTs. Maybe this is going to be very destructive, what I'm going to do here, but you know what? Oh well, we've already damaged components on this thing already. So if more gets damaged, too bad, so sad. Okay, I'm going to turn on the power, and we should see the 90 volts B plus on this line. So the line should jump up a little bit, but nothing else should go wrong, theoretically, unless that part is somehow damaged. I mean, it didn't really test in the tester, but well, let's see what happens. Okay, B plus is running. So the set's off right now, right? So that line jumped up. I just turned the power back off again. So it should slowly fade. Yeah, 62, 50 volts. All right, it's down to 12 volts, but I'm going to turn it back on. It's going to jump back up to, it says 100 volts, but we know that it's like 97. All right, everyone, are we ready? Are we ready to see what happens here? I'm going to turn it on very briefly and then turn it back off again. Okay. Well, there were pulses. I turned it off, so I don't think it died. I think the set is still running. Yeah, we're still at 100 volts, so nothing shorted. Unfortunately, my wireless mic died, so I'm going to be doing some voiceover. So that looks really promising. We had a proper looking waveform, and right now the horizontal and vertical deflection coil is not connected. That means that the waveform isn't going to be as high because it's not going to be generating any kind of high voltage. But this looks really promising. What's cool is I touched the heatsink and it's not even warm. It's cold to the touch. That's very different than how it was before with the other horizontal output transistor. It got hot very quickly. So really, the next step is to connect the horizontal deflection yoke, so that way we can see if we can get that full waveform coming from the horizontal output transistor to the flyback and the deflection coil, which would be the next step in getting this set working. Anyhow, what we have here is this multimeter is connected to the 25 volt rail. 25 volt rail has a capacitor. It's a 470 microfarad, and I am on the positive side of that capacitor with this multimeter right there. That's that red probe. This is still connected to the collector on the horizontal output transistor, the new one. Damper diode is removed, of course. The deflection yoke is connected to the horizontal side, so that means we should have full voltage. And just to make sure that, yep, the little anode cup is still in the middle of my thick glass, just as an insulation thing, and the neck board is disconnected. So theoretically, when we turn this on, we should see B+, and when I go to turn on the power, the switching thing, then this should run, and I'm gonna switch this, I'm gonna do a manual mode on this, so we can get to see if we have 15 volts on there without it auto-ranging, because this is kind of slow at auto-ranging. So we should see, not 15 volts, 25 volts or thereabouts on there if everything is working. And if we're seeing the 25 volts, that means that the whole switching circuit is working. And remember on here, we're set to 250 volts per division. It should be going up to like 1,000 volts. So the waveform should go pretty high on there, but I don't really know exactly how high it should go. So are we ready? Just double check things are connected, the grounds are connected. Okay, so B+ should come in now. There it is, 112 volts. 3, 2, 1. Wow. What did that have? I couldn't read the multimeter there. Was that 20 volts? 27 volts? 25? Is this thing working right now? Do we actually have fully functional set? Wait a second, wait a second. Why? Oh, I mean, the damper diode. I took the damper diode out. That could be our fault. Wow, wow. I'm gonna turn this on again. By the way, when this runs, I hear all this like noise coming out of the high voltage anode cup back there. Like it's like high voltage tension noise, kind of scary sounding noise actually. I turned off the main power to the set, so that's just dropping. I'm going to touch the heatsink real quick. Cold. That's the horizontal output heatsink. It's cold. It's freaking cold. You gotta be kidding me. All right, I'm gonna turn this back on again. So B+, there it is, 112 volts. Turn this on. Yeah. Okay, I'm just so freaked out that it's gonna blow up again. I'm not even looking at the max voltage there. Let's try to do this again. Peak to peak. 762 volts. That is way, way better than we ever had before. That's a good sign. I think I need to just hook this all back to the CRT because this might actually work. Let's get the camera zoomed out here. This might actually work unless, well, I know I tested the CRT. There's no shorts here. So hooking up the neck board should be fine as well. Wow. I am so freaking blown away that this thing is just working now, that it's just working. How is this even possible? I mean, it's not like we're actually running with the CRT under load. It's not actually turned on or anything. So this all could still go very wrong because we still could have a fault somewhere, but it seems like the set is running. What I'm gonna do is take my high voltage probe here, and I don't know if like that anode cap retains any voltage. So it doesn't show anything. I mean, the set's off, it's unplugged right now. I mean, there's nothing that showed up on the meter, at least that I saw. I just want to make sure that I don't get a zap by touching that, but since there was potentially 20,000 volts on this, and it wasn't going into a capacitor like the CRT or anything, it just was making a weird noise, like a clicking noise. It sounded evil, like it wanted to zap you. Because I don't want to do too many things at once, I'm just going to take like one step at a time. High voltage anode is connected. I have the ground lead reconnected from the CRT back to the neck board because that ends up grounding this board to the CRT through all these ribbon cables. I'm not going to plug this in, and I'm not going to plug in the vertical. There's no danger of drawing a line across the screen because without the filament being lit from this, there's no way there's any image that's going to be generated, even if there's high voltage on the TV. So we can check the waveform on the horizontal output transistor. So there's our B+, 112 volts. I'm going to turn on the set, listen for high voltage, and turn it off very quickly. Okay, it's freaking working. We have total high voltage. You gotta be freaking kidding me. Power's off, obviously. I shut the set immediately back off again. Yeah, I mean, this was up to, whoops, the anode cap just sort of came off. Let's discharge the CRT and reconnect that. I didn't have it connected properly, obviously. Okay, set is discharged, so it says 0 volts. So let's hook this back up again. Yeah, this was running. This was freaking working. So what I'm gonna do is I'm gonna keep the probe in there, and we're gonna see if we have like the 24 kilovolts that we should have on here. All right, here we go, 3, 2, 1. Yes, 24 kilovolts. It was right on the red line. It was right on the red line. This is just working. It's magically working. I'm gonna shut the power off. I need to keep reconnecting things. Let's do the next phase and let's connect up the vertical deflection. I'm still not gonna plug the neck board in though. I'm just gonna plug in the vertical deflection. The power is currently off to the whole board. Okay, vertical deflection is now connected. This is disconnected still, so we're just doing one thing at a time. And I'm gonna watch this time. Let's turn the power back on. Maybe the extra load of the vertical deflection, maybe that's where the problem lies in this coil. I don't know, we'll see very quickly here. Nope, it's working. So I just turned it off real quick. I'm gonna turn it on. I really need to pay attention to what the peak to peak is on here. 775 volts. It looks like the maximum voltage on that switching waveform, but I totally hear the high voltage happening on the set. So again, luckily nothing can really happen with this disconnected. So I'm gonna turn the power off. I'll let the B+ bleed away. Okay, so we have the last piece of the puzzle, which is the neck board when it comes to load on the entire circuit. That's it. This is it. The flexion yoke's fully connected, high voltage anode is fully connected, and the CRT is charged right now, so I'm gonna be careful not to touch in that area. This thing is off right now, but when I turn this on and we get that good 775 volt waveform on the oscilloscope on the collector, then everything we need for an image is going to be there. So should I turn on the power? Yes, here we go. 112 volts. 3, 2, 1. Yes, I'm assuming it is fully working, and there was probably an image on screen there. I mean, we had normal, everything was normal on here. This looked perfect. No, no issues. So the power's off. B plus is dropped away. So yep, nothing is showing on the scope now. I'm gonna turn this and be careful. The CRT is currently charged up. And here it is, the camera repositioned so you could see the set. Make sure all the cables are clear. Yeah, the scope is still connected to the collector, so I can keep an eye on the waveform. Okay, here we go. B plus is there. And I gotta reach around here and very carefully push the power button. Okay. Uh-oh, uh-oh. Obviously, we were not getting vertical deflection there, but we had an image. We had a freaking image, everyone. That is unbelievable. Okay, let's check what I did wrong here. Is power off? Yes. One thing I'm going to do is I'm going to use the multimeter here just to double check that there's continuity from the connections on the board to the deflection yoke, the 2 pins on the top for the vertical, that is. Obviously horizontal is working fine at this point, which is unbelievable. But let's just make sure that there is good continuity all the way through, because, you know, obviously someone was messing with this. So that's good. We have good continuity there. Okay, yes. So that means the deflection yoke is connected to the board correctly, but we don't have working vertical deflection for some reason. Is this some component that I removed or broke or something? I'm just going to quickly give it a try one more time. See if we have vertical deflection. Okay, I'm ready to turn off the TV in a second here. Yep, still have the line. Okay, well, look. Sorry, I'm laughing so much. I cannot believe this TV is just working now. I mean, it's not fixed, but we have high voltage. We have good horizontal deflection. We are just missing the vertical. We obviously have cathode drive. I'm assuming what we're seeing there is a blue screen, probably from like the fact that the video inputs are selected or whatever. What I'm going to do to allow this set to run for longer is I'm going to turn down the screen voltage. That way we actually won't burn the screen by letting it run like that. So let's give it a try. I just turned down the screen voltage. It's funny, now that the CRT is charged up, I can't really hear if the CRT is running or not. Oh, interesting. It turned itself off. It went into like a protection mode. Well, I wonder what that's all about. Maybe we're missing one of the voltage rails. Okay, so I'm going to turn this on. I just want to get this screen set to a point where it's not going to damage the CRT. There we go. Okay, that's nice and low, and there, it turned itself off. Okay, well, it's protecting itself, probably because it knows the vertical's not running, and a set like this, if you don't have the screen turned way down like I do, it will burn a line in the set, and that is not good. But it feels so good to finally make some progress on this thing. I was really, really close in this video to just giving up entirely on this because I couldn't figure out what was wrong. My only hypothesis here is this damper diode I took out is somehow bad, and as the voltage went up, it started to conduct, and that would cause excessive current drain on the horizontal output transistor, taking out probably the first one and the second one. Or was it really just that that second horizontal output transistor I put in maybe was bad already, or was so ill-fitted to work in this set that it blew out immediately? I just don't know. I just don't know enough about it. But it seems this Sanyo, which I think is the maker of this horizontal output transistor, with the built-in damper diode, obviously is okay working in here. Let me just turn off the power to this, because every time I've touched the heatsink that the horizontal output transistor is on, it's totally cold. It's not even warm at all. So it's obviously operating in an okay zone where it's happy and it's not drawing excessive current, which is obviously what took out the second one. Anyhow, this is really curious. So yes, anyone has any ideas about this damper diode? Is that possibly the issue? Or did I just have bad luck with that second transistor? And if I had the correct horizontal output transistor the first time, the set would have worked and I would have skipped all that excessive troubleshooting that I did? Maybe. As far as the collapsed vertical, we know the deflection yoke has some inductance because the LCR meter measured it. Also, I saw that through the multimeter, when I was just toning out that the connection was good, I could see it was like, less than 1 ohm when I had a direct connection through the wire to the board. And on the other side of the vertical deflection yoke, I had like several ohms or whatever, so maybe 15 ohms or whatever it was. It just shows that it was going through that coil. So the coil itself is connected. Now, I didn't ring out the vertical, but I don't think that necessarily matters, because if it had some shorter turns, we'd probably get some amount of deflection and it would like fold over or whatever. It's acting as if there's 0 drive. So it's quite possible, and I'd see this by looking, that maybe one of these auxiliary voltages that's generated is not working. Like there's another bad diode or something that I did while I was probing around. I've manipulated this board so much I could have broken something. Maybe whatever powers up the vertical section is not getting power. There's some diagnostic troubleshooting to do there, because now that we've gone ahead. The fact that the TV protects itself, though, well, we'll have to look into that whole circuit. It's quite possible the microcontroller monitors the V-Sync pin coming out of the vertical deflection, and if it doesn't see it because it doesn't want to burn the screen, just shuts off the TV, which is probably what's happening right now. Some of the Philips TVs have an LED on the front that will flash to tell you, hey, this is the error code, and you can look it up. This one does not. They wanted to save that like 10 cents or whatever it was to not install an LED, so you have no way to know what's wrong, and you got to go through the troubleshooting steps. But I feel like I've made amazing progress on this set. I finally have it generating high voltage. I can't state how happy I am about this. And I guess there's going to be a part 4. So I'm sorry for the constant CRT videos on the second channel, but it's been fun exercise trying to get this old thing working again, and finally some progress. Finally. I'm very excited. I'm very, very excited. So if you enjoyed this video so far, thumbs up. If you have thoughts about the damper diode or what went wrong, why I got stuck on that other horizontal output transistor, definitely comment down below. Let me know what I was doing wrong or right about testing the ringing on the various components like the flybacks and stuff. And I did learn some stuff that the flyback from that other part set is definitely not compatible with this. And I feel like if I put it in there, it would have actually damaged stuff on here, because that pin 7 is connected directly to B+, and as soon as I turned it on, it would have sent 95 volts into a bunch of parts of the circuit that definitely don't want to see 95 volts. So yep, that's good. Don't just swap flybacks because they fit. Probably will destroy things unless you know for sure it's compatible. And yeah, thanks to my supporters, and there we go, second channel video. That's gonna be that, so stay healthy, stay safe, and I'll see you next time. Bye-bye.